So here's another kind of problem that you'll run across in a lab that we'll probably do this week, but we may end up doing it next week. In that problem, what you do is you collect a gas over water. So what does it mean to collect a gas over water? So imagine if you have a bottle like this, right, and you're going to use a long tube actually. But if you have a bottle like this and you fill it up with water, that's not a very good bottle. Let's do it like this. There we go. So this is your bottle. You fill it up with water and then you submerge it in water like this, and then you put a tube in it like this, all right? Now this tube will run to a reaction, and that reaction is going to introduce gas as bubbles into the bottle. You can trap this gas from these bubbles in the bottle. So that's what we mean by collected, a gas collected over water. So it gets this kind of term cow, right? Now, in these cow problems, what we find is that the vapor pressure, or the partial pressure of water, so we call it the vapor pressure of water is proportional, or is related to the temperature. It's actually exponentially related to temperature. And we actually ran into this phenomenon before. This comes from chapter 15 in Le Chatelier's principle. If you have water and it's in the liquid state like this, it's in equilibrium with water in the gas state. This is the vapor, right? So this is the vapor pressure of water. This reaction is endothermic because remember the gas state's above energy, higher in energy than the liquid. So I'm adding energy like this. So if I add energy to this reaction, that is, I increase the temperature, and that's what we're seeing here. If I increase the temperature, it causes the equilibrium to shift to the right, and then what happens is the vapor pressure of water increases. So at 10 degrees Celsius, which is relatively cold, right, that's 9.2 millimeters of mercury. Out on a very hot day, it might be 5 times that. This would be 40 degrees Celsius. You could have 55 millimeters of mercury. In terms of vapor pressure of water. If you've ever lived in the South, or like worked in the fields after they water, or live sort of in the tropics, what you find out is when it's hot, it's humid. It's super humid. The reason for that is as the temperature increases, there's so much water in the surrounding areas that the vapor pressure of water increases. And so it displaces, right, a lot of the air and fills it with water vapor. So it's really muggy, and like you go out there and it feels all wet all the time. You can't sweat because in order to sweat, right, you have to evaporate water off your skin. But if there's a lot of water vapor in the air already, it suppresses that equilibrium, and so you can't sweat and cool down that way because of all the water vapor. So anyways, having said that, right, one of the very common problems is to collect a gas over a liquid and then try to calculate how many moles of gas you collected in that process. So I have 125 milliliters of methane. It's collected over water at a total pressure of 758 millimeters of mercury at 30 degrees Celsius. What is the partial pressure of methane in the mixture? That's the first question. And how many moles of methane were collected? So I'm going to do this problem in 2 parts. The first part is just to calculate what the partial pressure of methane is. So P total is going to be the P of the water plus the P of the methane. So I'll call that M like that, okay? And this is Dalton's law of partial pressures. And basically, if I add the pressures up, it equals the total pressure. So then I can solve for the pressure of methane by saying P total the pressure of methane is equal to P total minus the pressure of water. So this is at 30 degrees Celsius. So at 30 degrees Celsius is 31.8 millimeters of mercury. My total pressure is 758. So this will be 758 millimeters of mercury minus, and then 31.8 millimeters of mercury. So I went and calculated that value. It's 726.2 millimeters of mercury. So that's the pressure inside the bottle that's being exerted by the methane. Now, to figure out how many moles of methane there are, you use the ideal gas law. So you say P, V, N, and T. My pressure is 726.2. By the way, it's significant to the 6 there, so 726.2 millimeters of mercury. Now, you should recognize at this point that needs to get converted over to atmosphere, so it's going to be 1 atmosphere over 760 millimeters of mercury. The volume is 125 milliliters. That'll be 0.125 liters. So I just did that conversion without showing you. Okay. I'm looking for the number of moles. And the temperature is 30, so that's going to be 30 plus 273. That's 303 Kelvin. So now I can solve for PV equals nRT for moles. I've done this before, so that just comes out to N and then PV over RT. And now I can plug the values in and do the calculation. So I'm going to leave that as an exercise for you to do. I'll write the answer on the slide in a few seconds, but you should set it up and make sure you can get that answer. And so that's the answer for that calculation. Okay, so go ahead and try setting that up to see that you can get it. It's a little tiny number because it's not a really large volume. I don't know if you remember the calculation we did before, but at atmospheric pressure, at standard temperature and pressure, a mole of gas occupies 22 liters, and this is only a fraction of that. It's 0.125 liters, right? So you expect this number to be relatively small because it's a small volume.